Hello, good morning. I want to say that it's a privilege and an honor to be part of this first ever ISMRM African chapter meeting. I want to express my thanks to the organizers for spending a lot of time to get this program going on. I want once again to thank them for inviting me to make a presentation at this meeting. A little bit about myself. My name is Asamoah Bosomtwi. I'm originally from Ghana, and at the moment I work at the Georgia Cancer Center to Augusta University in the USA as an MRI scientist. When I was given this privilege to talk about introduction to MRI physics, I asked a few questions to see what will help me to make the presentation so that everybody who will be at this meeting will be able to get something to take home. I asked myself a few questions. The question that I asked myself, one was, what is my audience? Are they all students? Are they faculties? Are they medical professionals? Are they MRI technologists, MRI physicists, engineers, or ordinary citizens? The next question that I asked was, what is their level of physics, and how deep do I need to go? Also, I asked another question, that do I need to just look at the classical physics or do quantum physics to talk about the quantum mechanical properties of protons and so on and so forth, looking at all the equations? Or do I need to just brush aside the equations and go and talk about the phenomenon of the proton that takes place? So what I've decided is just not to go much into the equations talking about quantum mechanics or look at a lot of mathematical equations, but we will look at a brief thing that is associated with the MRI physics. And if anybody is interested in getting the detailed equations, I'm more than happy to sit down with you and go through those quantum equations with you. So the outline that I will look at is a brief history of MRI, talk about basic physics associated with MRI, talk about block equations, look at relaxation and tissue contrast. But here I'm not going to go into much detail because just after this talk, Professor Webb is going to talk about MRI techniques, pulse sequence. So I will leave that to Professor Webb to take care of it. We can't talk about MRI without first talking about the discovery of NMR. NMR, that is the nuclear magnetic resonance, was discovered in 1938 by Professor Rabi, and he detected the MRI absorption in a molecular beam. With this discovery, Professor Rabi was given a Nobel Prize in 1944 for his contribution into particle physics. The NMR is a physical phenomenon where a given nucleus absorbs and re-emits electromagnetic radiation. We also use MRI to indicate the way NMR is used to produce a medically useful image. So this is why the discovery of NMR is very important to MRI at the moment. We continue with the history of NMR by looking at 1945, where Felix Bloch detected the NMR absorptions in paraffin. The same year, Edward Purcell also detected the nuclear induction signal in water. In 1946, both Purcell and Bloch independently devised virtually identical methods in measuring nuclear magnetic moments. And this led to them getting a combined Nobel Prize in Physics in 1952. There were a series of experiments that went on during that time, and in 1971, the Median tried to use the concept of NMR to detect tumors in human beings. He tried and designed a big magnet whereby he could detect tumor in human body. In 1973, Letterman suggested that we can use NMR to generate images, whereby he introduced the idea of sweeping the magnets through a gradient field to generate images. In 1975, Ernst also developed the 2D NMR method, and that earned him a Nobel Prize in 1991 in chemistry. Sir Peter Mansfield also proposed echoplanar imaging that is used in current clinical MRI scanners. And in 1977, clinical MRI scanners were patented. This also led to Paul Letterman and Peter Mansfield getting Nobel Prize in physiology in 2003. MRI rely on nuclear magnetic resonance phenomena. The N means that the signal is coming from the nuclei of an atom, and especially the odd number of nucleons. And it usually comes from the nucleus of the hydrogen atom of the water molecules that are found in the human bodies. The M is the fact that we rely on the magnetic field, and also we try to get the magnetic moments measured from the magnetic properties of the hydrogen atom. The R is the fact that we try to look at the interaction between the magnetic field and the radio frequency, which is part of the electromagnetic spectrum. And we look at how the frequencies will be resonating. So we look at resonance frequencies. That is why we have the NMR in the MRI system. One may ask why the name changed from NMR to MRI, and the explanation is that in the 80s, the term nuclear was given a bad connotation, and people were afraid to use the term nuclear. And for that matter, the N was dropped, and we had the magnetic resonance imaging. Here we will have a short overview to look at what we need in an MRI system. So for our clinical MRI system, as you see in the panel here, we will have various components of the MRI system. We have the magnet itself, the big magnet. Then in the magnet, we have a gradient coils that will take the three orthogonal planes, the X, Y, and the Z direction. Then we have the RF coil. So looking at the diagram above, we have the outside is the main magnet. Then we have the gradient coils. Then we have the RF coil. All of them is connected to a computer where signals are detected, and then the computer reconstruct the images. As this is a simplified form of the MRI system. Here we have a patient lying in the big magnet, and the B naught is the magnetic field for the external strong magnet. Then we have the B1, which is the radio frequency that we apply here. So here, what we normally do is we have given sequences that we do. However, I will just say that we take a patient, we put the patient in the big magnetic field, leave the patient there for a few minutes, then we transmit radio wave into the subject. After the radio wave is transmitted into the subject, it is turned off. After turning off, the subject is going to retransmit the radio wave. So we have receivers to receive the radio waves. After we receive the radio waves, within a short time, we will record this radio wave data versus time. Then this data is sent into the computer, which is reconstructed these radio waves into an image. Here we will talk briefly about basic physics, and then we will look at various components, how the physics is applied in these components of the MRI, and we will continue from there. So the first thing we will look at is the main magnet, which is B naught. And it's very, very important to have a B naught because the B naught magnetizes the patient. And without the magnetization, we will not be able to get any signal. So the B naught is very essential for the MRI signal production. The B naught is also proportional to something that we will have to look at. The B naught is proportional to the artifact to noise ratio, signal to noise ratio, precession frequency. Then it's also look at the susceptibility effect and the chemical shift. Other factors that are related to the B naught is that it affects our T1 and our T2 star. The magnetic field B naught is very strong and is measured in the unit of Tesla or Gauss. And we have 1 Tesla is equivalent of 10,000 Gauss. To compare the magnetic field of the magnets that we use in day-to-day clinical settings, we will compare it with the Earth magnetic field. Earth magnetic field is about 0.5 Gauss. So when we take our everyday clinical scanner, which is about 1.5 Tesla, we found out that it's about 30,000 Earth magnetic field. If you are using a scanner of 3 Tesla, it goes to about 60,000. And then presently we have some magnets that we use in the clinical research, which has 7 Tesla, and it's about 140,000 times the Earth magnetic field. One thing that I will let everybody know is that our magnet is always on. So to any ordinary person, you might think that when the magnet is not in use, it's off. The magnet is always on. It's a superconducting magnet, and it's always on. So if you are going to work with the magnet please be careful and know that our magnet is always on. Thank you. Let's switch gears and look at our high school basic physics, where we look at the electromagnetic spectrum. We have the electromagnetic spectrum. Here I have the energy, frequency, and the wavelength. And we have the X-ray with a frequency of 10 to the power 19 up to 10 to the power 18. And you have the UV rays, visible light, infrared, microwave, and radio waves. The radio waves and the TV is around 10 to the power 8 for the frequency. And this is the region in which we use our MRI radio waves. So the radio waves that we are generating, the pulse that we generate normally comes from where we have the radio wave signal coming from. So it's not in the X-rays where we get ionizing radiation. The radio waves that we put in patient is not going to ionize anything. So I want you to be rest assured that when you do MRI, you are not getting any radiation getting into your system to cause any problems for you. We continue our basic physics by this time looking at the nuclei. The nuclei, or that is the plural, but when you look at the nucleus, there is a need to have two properties of a nucleus. The nucleus has a spin and a charge. The nuclei is made up of a proton and neutrons. Both the protons and neutrons have a spin of 1/2. However, neutrons have no charge, whereas protons have a charge, a positive charge. When you have a pair of spins, the spins are aligned in opposite way, and for that matter, the atoms that have the same number of spins, the spins cancel out, and for that matter, you are not getting any net spin coming out of that. When you have a proton and a neutron, the net spin is 0. Good MRI nuclei are hydrogen, carbon-13, fluorine-19, sodium-23, and phosphorus-30. However, most of the clinical scanners, we use hydrogen protons. And then somebody may ask why we use hydrogen protons. Because hydrogen is more abundant compared to the other nuclei that we have listed above. So most of the signals that we measure in our everyday clinical scanner for humans is hydrogen proton. And somebody may ask why we use hydrogen. When you take adult human body, it is approximately 53% water, and the water is approximately 11% hydrogen by mass, but 67% hydrogen by atomic percentage. Hydrogen is present in virtually all biological materials. Therefore, it is good that we use hydrogen in doing our MRI signals. Looking at the table that we have here, you see the hydrogen has 100% relative percentage in soft tissue. The next abundant nuclei that we have is sodium, which is 0.09%. So looking at 100% compared to 0.09, it is better that we rely mostly on hydrogen to get our MRI signal. Protons can be regarded as a small, freely suspended bar magnet spinning rapidly about its magnetic axis. The positively charged hydrogen proton spins about its axis and acts like a tiny magnet. Due to the combination of the charge and the nuclear spin, these nuclei behaves as magnetic dipoles. The proton also has a mass which generates an angular momentum when it is spinning. Thus, the proton magnets differ from the bar magnet in that it also possesses angular momentum caused by the spinning. This is an example that when we have a hydrogen, helium, and helium-3, the helium has 2 protons, 2 neutrons, and for that matter, it will have a spin of 0, whereas hydrogen has only 1 proton, so it has a spin of 1/2, and helium-3 will have a spin of 1/2. With no external magnetic field, hydrogen protons are oriented randomly. Hence, the net magnetization is 0. In the presence of strong magnetic field, these randomly moving protons align and spin in the direction of the external magnetic field, similar to when we have a compass that aligns in the presence of Earth's magnetic field. Some align parallel and others align anti-parallel to the external magnetic field. When these protons align along the external magnetic field, it is not only that it's rotating on its own axis, but it also forms a cone, and the movement of the axis of rotation of the proton is what we call precession. The number of precession of a proton per second is called precession frequency, and it's usually measured in hertz. Precession frequency is directly proportional to the external magnetic field. So the stronger the external magnetic field, the higher the precession frequency. In the absence of angular momentum, a magnetic dipole will align with the external magnetic field. For the magnetic dipoles with lower energy states will be parallel to the external magnetic field, whereas the higher energy state will be anti-parallel to the external magnetic field. With angular momentum, the magnetic dipole exerts a force known as a torque, and is given by the torque is equal to the cross product of the angular momentum and the external magnetic field. And the energy is given by this classical equation, which is the dot product of the magnetic moment and the external magnetic field. The spin angular momentum and magnetic dipole moments are related by the equation mu equals to gamma times I, where the I is the angular momentum. At the same time, the angular momentum is also related to the torque, which is the rate of change of angular momentum. So putting these two equations together gives us this relation. Without going through a lot of mathematics, the solution is given by gamma, omega equals to gamma times the B naught. This solution is what we call the Lamar equation, where we have the omega being the precessional frequency, gamma being the gyromagnetic ratio, and B naught being the external magnetic field. The precessional frequency is dependent on the strength of the external magnetic field. The stronger the external magnetic field, the higher precessional frequency. The gyromagnetic ratio is specific to each type of nucleus. For proton, it's 42.58 megahertz per Tesla. Here we will talk briefly about block equation and how it's going to help us in our signal acquisition. I want to talk about the block equation from beginner's perspective. The block equation can be regarded as the equation of motion for the nuclear magnetization. This is partially considered as a phenomenological in origin. The time these equations were developed, it was based rather on classical picture of physics, and physics has evolved since then, and we got into quantum mechanical theories, and for that matter, the equations might not hold in this. However, with some assumptions, we are able to use these block equations to explain the concept of the MRI. The block equation was done before we know of K-space. Also, the equations were developed before any imaging was done. It was solely due to use it to measure signals in the physical experiments. The block equation is described as how magnetic moment changes with time and is written in this differential equation form. Expanding the cross product, you can write the block equations in x, y, and z components, and it's written in that form. If you prefer to use just the cross product, you can use that. However, we can write it in different form if you prefer to get it in the Cartesian coordinates. In experiments, we observe mono-exponential response for the block equation with the relaxation terms. This mono-exponential response does not mean that the block equation is wrong, but it's an approximation. In these equations, we add the relaxation term that is proportional to the rate of change of the magnetization in the case of the transverse relaxation. The relaxation term is proportional to the rate of change of magnetization, meaning if we have more T2 relaxation, the decay is typically exponential. For the longitudinal relaxation, the rate of change of magnetization in the z direction depends on T1 relaxation. That means that the magnetization does not decay, but it recovers to equilibrium magnetization M0. These set of differential equations with their relaxation terms cannot be solved analytically. Hence, we have to consider a special case. For the special case that we consider is that in the x1 plane, the magnetic fields there are very small compared to the B0, and for that matter, we can approximate them to be equal to 0. With that, we will have the equations reduced to the expressions shown here. These equations can therefore be solved analytically, and the solution is as follows. The solution for the special case of the block equation is written in details for you to notice the harmonic terms in the mx and then mz, the transverse component of the equation. For the transverse component, we have the precession term, which is due to the omega, the harmonics that is there, and then we have the decay term due to the T2. The longitudinal component or the longitudinal part, the MZ, which does not precess but is stationary, will only have the T1 term that recovers to the M0. For our longitudinal part, we also see that the parameters depend on the initial conditions that is given at time t0. These initial conditions allow us to start a typical MR experiment. For example, when we have t at time t0, if we have mz at 0, we get only the term for the saturation recovery. And if we do have mz to have a value of minus m0, we get the condition that is the inversion recovery. All that we have talked about for solving the block equation is being considered in the lab frame of reference. However, I want us to switch gears a little bit and look at the rotating frame. In the rotating frame, the Lambda frequency appears to be stationary. Therefore, the omega will be 0. And in that case, the block equation will be missing all the oscillation terms. This is the equations that, the solutions that you see people presenting. However, this is only true when you consider the rotating frame. The final part of my talk, I will look at the relaxation processes. When RF is turned off, the hydrogen proton slowly returns to their natural alignment within the magnetic field and release their excess stored energy. This is known as relaxation. The question is, what happens to this released energy? What happens is it releases as heat, and also sometimes it's exchanged and absorbed by other protons, and also it's released as radio waves. The process where hydrogen protons slowly recover T2 decay. T1 relaxation is sometimes also called spin lattice relaxation. After a 90 degrees RF pulse causes longitudinal magnetization to become 0, over time the longitudinal magnetization will grow back in the direction parallel to the main magnetic field. The rate at which this longitudinal magnetization grows back is different for protons associated with different tissues, and this is fundamental source of contrast in T1 weighted image. Looking at the light gray component, you see that when the RF pulse is applied, the T1 relaxation is 0 and it starts growing gradually, and it grows in an exponential decay for several T1 to reach equilibrium position. T1 is a parameter that is characteristic of a specific tissue and is related to the rate of regrowth of longitudinal magnetization. The magnetization of a tissue with different values of T1 will grow back in the longitudinal direction at different rates. As shown in the figure, you see that fat has a shorter T1 compared to water. T2 relaxation is also sometimes called spin-spin relaxation. And that is the magnetization in the transverse plane. After a 90 degrees pulse rotates longitudinal magnetization into the transverse plane, the magnetization is called transverse magnetization. Immediately after application of the 90-degree pulse, the magnetization is maximized. Then it begins to dephase due to several processes. One, there's a spin-spin interaction, there's magnetic field inhomogeneity, magnetic susceptibility, and the chemical shift effect. Here, any spin close to another will experience the magnetic field due to the other spin, and this slightly alters the precessional frequency. And this is one of the things that goes on that causes the frequency, the precession to decay, and you get the dephasing. The loss of the phase coherence results in the exponential decay of the signal in the transverse plane. After the application of the RF pulse, the transverse component of the T2 relaxation reduces towards zero. Different tissues have different values of T2 and they dephase at different rates. T2 is a characteristic of the tissue and is defined as the time that it takes the transverse magnetization to decrease to 37% of its starting value. We cannot talk about the MRI without talking about the time of repetition, the repetition time, and that is the time between successive excitation, or the time from application of one RF pulse to application of the next RF pulse. That is what we call the repetition time. Repetition time determines the amount of longitudinal relaxation that is allowed to occur before the next RF pulse is applied. Echo time is the time between the excitation and the data acquisition. The echo time determines how much decay of transverse magnetization is allowed to occur. Thus, TE, that is the echo time, controls amount of T2 relaxation that has occurred when signal is read. Magnetic field inhomogeneity causes transverse signal to decay more rapidly. The exponential decay time for this process is called T2 star. The factors that affect magnetic field inhomogeneity is imperfect shimming, and then also the induction of a perturbation field due to susceptibility difference at the tissue boundaries. The T2 star is related to the intrinsic properties of the transverse magnetization time constant T2 and the field inhomogeneity as given in the equation above. Thank you. Thank you very much. Any questions?